Hi everyone, hope everybody is doing well. I'm gonna go ahead and explain you homework 8. That's from chapter 8, homework. So let's go ahead and do number 1. Each electron in an atom must have its own unique set of quantum numbers. And who said this statement? For this one you can refer to the lecture notes, and this is the Pauli exclusion principle. So the correct answer for 1 is C. Okay, and for the number 2, which one of the following statements about orbital energies is incorrect? A is inner electrons shield outer electrons more effectively than do electrons in the same orbital. That's true. Inner electrons shield outer electrons more effectively than do electrons in the same orbital. What that means is, now we know that the electrons are in orbitals, right? For example, we can consider, let's say if this is your nucleus and then you have shells, okay, and then you can have some electrons. These electrons are in the same level, and then you can have some other electrons in the inner levels. So if you have an electron, let's say somewhere here, the shielding means that it would not let the nuclear charge fields. So the inner electrons means, okay, let's do. So these are the inner electrons. Though they shield the outer electron more effectively than they do shield from the same level. So that is a correct statement. Okay. And then we are looking at the one that is incorrect. So the first one is correct. Inner electrons shield outer electrons more effectively than do electrons in the same orbital. B. The splitting of sublevels in many electron atoms is explained in terms of the penetration effect. Yes, that is true. So we talk about the penetration as the sizes are going to be different, as well as the shapes of the orbitals are going to be different. Depending on the shape of the orbitals, they could be more closer, or it could be a little bit further away from the nucleus. So we talk about that as penetration effect. So the penetration effect is going to affect the splitting of the sublevel energies. Okay, and C, in the hydrogen atom, the energy of an orbital depends only on the value of the quantum number n. That is true because hydrogen has only one electron. Because it does have only one, that electron is in the s orbital. So the energies only depend on the principal quantum number n. Otherwise, it can also depend on the shape of the orbital. But since hydrogen has only one electron, it would only depend on quantum number n. Okay? And then the energy of a given orbital increases as the nuclear charge Z increases. That's not correct. The energy of a given orbital decreases as the nuclear charge increases, meaning now the electrons are going to be more attracted towards the nucleus, making lower in energy. So D is the wrong one. Okay. In many electron atoms, the energy of an orbital depend on both N and L. That is true. Meaning not a hydrogen atom because it has only one electron, but if you have an atom which has more electrons, meaning it can have different types of shapes. Shape is defined by the value L. So the shape and the principal quantum number N both decide the energy of an orbital. So the wrong one is D. Okay, for number 2. And for the number 3, the effective nuclear charge for an atom is less than the actual nuclear charge due to, you know this one, due to shielding. Okay. And number 4, in many electron atoms, which quantum number specify the energy of an electron? Many electron meaning more than one electron. So it is N and L both. N is the principal quantum number and L define the shape of the orbital. Okay, this N and L both. And number 5, electrons added to atomic orbitals of the same energy will remain unpaired with parallel spins until the subshell is more than half filled is a statement of whose statement is that? Again, you can find out these from the lectures. Okay, that is Hund's rule. And number 6, which one of the following statements about atomic structure and quantum number is incorrect? Number 6, let's say for n equals 4, the largest possible value of L is 3. Okay, so let's look at that one. N equals for the largest possible value for L. That is true, right? Because, let me explain you that here. Let me see. Okay, for n equals 4, the largest possible value of L. So remember, when n can be a whole number. N could be n could be integer 1, 2, 3, 4, 5, 6, 7 like that. And L is going to be shape of the orbital, right? And n can be values from 0 to n minus 1. So if it is 0 to n minus 1, if n equals 1, n minus 1, 1 minus 1 would be 0. So n equals 1, you can only have L value 0. N equals 2, L could be 0 and 1. N equals 3, L could be 0 to 2 because 3 minus 1 is 2. This would be 1, 2, 3. Okay, like that. L values. So now the first statement is for n equals 4. So this is n equals 4. The largest possible value of L is 3. L, that is true. So the first statement is correct. Okay, and then the second statement, in a given atom, the maximum number of electrons having principal quantum number n equals 3 is 18. Okay, you can refer to the question, you have it in front of you. So in a given atom, the maximum number of electrons having principal quantum number n equals 3. Now let's see in the n equals 3 level, what is the maximum number of electrons that we can have. Now this 0, 1, 2, when n equals 3, 0, 1, 2 is the shapes of the orbital. Okay. So if n equals 3, L could be 0 to n minus 1. So that is n equals 3. So the L could be 0, 1. 3 minus 1 is 2. 0, 1, 2. So L 0 meaning that is a s orbital. L values. And L equals 1 means that's a p orbital. L equals 2 means that's a d orbital. Okay. So now each orbital can hold up to maximum of 2 electrons. But the ml, and we also learned about another quantum number ml, that can take the values from minus L, 0 to plus L. That is the orientation of the orbitals. Now for L equals 0. L equals 0. What are the possible ml values? That is going to be just 0. Right? And if L equals 1, what are the possible ml values? Minus 1, 0, plus 1. And if L equals 2, the possible ml values are minus 2 to plus 2, minus 2, minus 1, 0, plus 1, plus 2. So, S, we can have one orbital in this orbital. P would be 3, minus 1, 0, plus 1. And there are 5 d orbitals. Their orientations are minus 2, minus 1, 0, plus 1, plus 2. And all these orbitals can hold up to how many electrons? Up to 2 electrons. Now, how many orbitals do we have here? In the S level, we have 1. P level, we have 3. D level, we have 5. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, there are 9 orbitals. Each can hold up to 2 electrons. So, 9 times 2 is 18. So in 6b statement is in a given atom, the maximum number of electrons having principal quantum number n equals 3 is 18, which is a correct statement. Okay. And then the statement C is the following set of quantum numbers for a single orbital is not allowed. N equals 3. If n equals 3, the following set of quantum numbers for a single orbital is not allowed. If you have n equals 3 and then L equals 1, L could be 1. If n equals 3, let's say we are looking at n equals 3, okay? N equals 3, L equals 1, meaning L equals 1, and then ML equals minus 2. Do we have a ML value? ML, the possible ML values when L equals 1 is minus 1, 0, plus 1. And having ML equals minus 2, it says it is not allowed, which is true. If n equals 3, L equals 1, the possible ML values are minus 1, 0, plus 1. So ML negative 2 cannot be allowed, meaning C statement is also correct. Okay. And then the D, for n equals 4, the largest possible value for ML is 2. For n equals 4, let's say n equals 4. So if n equals 4, what are the possible values for L? L going to be 0, 2, n minus 1. N equals 4. 4 minus 1 is 3. So the largest possible L value, n equals 4, is 3. And it says L value equals 3. So if L equals 3, the largest possible L value is 3, what are the possible ML values? Remember, ML could be taking the values minus L, 0, 2, plus L. So the minus L would be, if L equals 3, negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. All of these ML values are possible. So the D is saying for n equals 4, the largest possible value of ML is 2. The largest one, ML, would be plus 3. So that's not the correct statement. So the wrong one is D. And then E, the number of orbitals in a given F subshell is 7. That's true, right? L, in fact, we were talking about L here. So we have L equals 3, which is a F orbital. So F subshell, 1, 2, 3, 4, 5, 6, 7. That's correct. Remember, always remember L values 0, 1, 2, 3. S, P, D, F. When L equals 3, that's a F orbital. So this is a F orbital. The possible ML values are all these. So there are 7 subshells. Okay. That's how we count the subshells, by counting the ML values. Okay. I hope you got it. Okay, so then the next question, number 7. In a single atom, what is the maximum number of electrons which can have quantum number n equals 4? In a single atom, what is the maximum number of electrons which can have quantum number n equals 4? So how do we find out this one? Again, let's look at n equals 4. We're going to find out the maximum number of electrons possible. If n equals 4, and then the L going to be again 0 to n minus 1. So the possible L values 0, 1, 2, 3. Right? And what are the possible ML values? Which tells us about the orientation that can take the form or the numbers minus L, 0, 2, plus L. If L equals 0, what are the possible ML values? Minus L, minus 0, 0. That's it. And what are the possible ML values for L equals 1? Minus 1, 0, plus 1. Minus L to plus L, minus 1, right? And then if L equals 2, possible ML values, minus 2 to plus 2, minus 2, minus 1, 0, plus 1, plus 2. And then if L equals 0, the possible ML values are minus 3 to plus 3, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Again, L is your S sublevel, P, D, F. L values represent the shapes of the molecule, the shapes of the atoms, that is S, P, D, F. And we have only one S orbital in a given level. And we have only one, we have P orbital. L value for the P orbital is 1. And then how many sublevels? There are 3 sublevels for P, meaning suborbitals. And for the D, there are 5 ML values, meaning there are 5 d orbitals possible. And for the F, there are 7 values, right? SPDF 1, 2, 3, 4, 5, 6, 7. So there are 7 sublevels or subshells for the F orbital. So, excuse me, 1. So what is the number of orbitals now we have if n equals 4? We have, here we have, this is 1, 1 plus 3, 4, 4 plus 5, how many? 4 plus 5, 9, 9 plus 7, 16. So there are 16 orbitals in the n equals 4 level possible. Okay, and so each orbital can carry 2 electrons. So 16 times 2 equals, equal sign, not multiplication, 32. So there are 32 electrons in a single atom. What is the maximum number of electrons which can have quantum number n equals 4? So the correct answer is 32. Okay, and if these orbitals, if the s orbital is in the n equals 4 level, we call it as 4s. This is 4p, 4d, 4f, like that. Okay, so there are 32 electrons possible in n equals 4. Okay, so the next one, and this one, the explanation for number 7. Okay, and then the number 8. Select the correct set of quantum numbers n, L, Ml, Ms for the highest energy electron in the ground state of potassium. Okay, okay, now let's look at the potassium. Okay, so let's see how we can find a potassium. You can refer to your periodic table and then you locate where the potassium is. So potassium is number 19 right there. Okay, and remember in the lecture videos you learned how to write the condensed electron configuration. Condensed electron configuration is you find out what is the noble gas prior to the element of interest. So here's potassium. The noble gas prior to potassium is argon. So you write argon and then you write the rest of the electron configuration. Now potassium is in which period? This is your period 1, 2, 3, 4. In the fourth period, the first group is always S1. The first S electron is being filled, and then the second S electron is being filled in the second group. And then if you are considering the main groups, these are going to be P. This would be P1 group, P2, P3, P4, P5, P6. That's how the electrons are being filled. Okay, now let's focus on the potassium. The prior to potassium noble gas is argon. So you write argon in square brackets and then you write 1, 2, 3, 4, 4, and this is S1 group is being filled. S1 orbital is being filled. So that's going to be S1, 4S1. So for potassium is going to be the noble gas prior to potassium is argon. You put it in the square bracket and it is in the 4s. So 4s1. Okay. And now it is asking select the correct set of quantum numbers. We want to find out the N, L, Ml and Ms values for the potassium. Now this one right here, the number prior to the orbital shape tells us the principal quantum number N. So in this case N equals 4. And then the S is defined by the letter L, which gives us a shape of the orbital. Remember, I've been telling you L values could be 0, 1, 2, 3 and the designated orbital shape is S, P, D, F. So if we are talking about S orbital, that means L value is going to be 0. So N equals 4, L equals 0. Okay, and if you draw the partial orbital diagram, this is your orbital. In the 4s orbital, there is only one s electron. That is the 4s1. Okay, now the next value is ml. Remember, ml could be minus L, 0 to plus L, between the numbers between these two. If L equals 0, what are the possible ml values? We have only one value, which is 0. The orientation of this one, this is 0. Okay, so ml therefore going to be 0. And then the last quantum number, which is a spin quantum number, ms, tells us whether the spin is facing up or facing down. If the spin, always the first spin in an orbital is facing up, that's plus half. And then the second one, when you are pairing it up, that would be negative half. And in our potassium, we have only one electron, that would be facing up plus half. So Ms is going to be plus half. So the quantum numbers for potassium 4s1 is N equals 4, L equals 0, Ml equals 0 and Ms equals plus half, which is C. 8. The correct answer is C. Okay. And then the next one, 9. Select the correct set of quantum numbers for the highest energy electron in the ground state of tin, Sn. Now let's go ahead and do that. Where's the tin? Let's look at the periodic table and let's locate where the tin is. Okay, Sn, somewhere here. This is tin, right there. And we can write the condensed electron configuration. And what is the noble gas prior to tin? That's going to be krypton. So you write krypton, and then the tin is in which period? So tin is in this period, which is 1, 2, 3, 4, 5. So after krypton comes the fifth period. By the time it goes to the tin, so this is your S block element. So the 5s1, 5s2 is being filled. After the S, 5s orbital, it's going to be the 4d. Remember, d starts in the third period. Okay, 3d. So this is going to be then 4d. Always the d going to be 1 less than the principal quantum number. So the principal quantum number is your this number, which is your 5, and then the d would be 4d. So d will be filled, since d can hold maximum 10 electrons, 4d 10, and then again these are going to be your p level, 5p. So 5p1, 5p2 when it comes to tin. So it would be krypton, 5s2, 4d10, 5p2 would be the condensed electron configuration for tin. Also you can refer to that. Here you see we were looking at tin, 5s2, 5p2. It's just showing the valence electron configuration, okay, in this diagram. And then you can refer to this one, how the orbitals been filled. Okay, you have available this one in your lecture notes. So you can see here 1s. So here's the 1s. In the period 1 you have only s, 1s, 1s2, and then the period 2 you have 2s, and then 2p. After 2s is done, so this is the 2p, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, and then goes to the 3s, and the 3s level also you have 3s goes to 3p, the third level. Okay, and then if you are in the fourth period, if you are looking at an element in the fourth period, first the 4s fills, then goes to the 3d. You see 4s, and then it crosses the 3d. 3d 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the 4p. Okay, now our tin is somewhere here in this particular place. So you get the noble gas configuration. Let's see how we're going to come there. So we have 5s. After 5s, you have to go through 4d. So this is your 4d, 4d10. All the d's are being filled. And then comes the 5p, 5p1, 5p2. So you can refer to this chart also to figure out the condensed electron configuration. Okay. Okay, so let's see. So we are looking at the tin electron configuration. We are in number 9. And then, oh, come on, 9. So the tin. So prior to tin, we have noble gas, krypton. And it's in the, tin is in the fifth period, so it is going to be 5s2, 4d10, 5p2. Okay, and it is asking select the set of quantum numbers for the highest energy electron in the ground state of tin. So this is the ground state configuration, meaning the electrons has not been excited. And the highest energy one would be, which one is the highest energy? It's always the highest principal, highest number. So we have two orbitals, 5s2 and 5p2. Between s and p, which one is lower in energy? S is more closer to the nucleus because of the spherical shape. P look like a dumbbell further away from the nucleus. So p has more energy compared to 5s. So the outermost electrons are going to be in p orbital. Okay, now the p orbital, how many p orbitals possible? P can have 3 subshells, remember, because L value, remember, always remember 1, 2, 3, L equals 0 is sp. I'm doing it over and over again for each question for you to get it. Okay, so L could be 0, 1, 2, 3, the corresponding shapes SPDF, and then the ML values are going to be minus L to plus L with the 0 in between. So for the ML values possible for L equals 0 is just 0. If L equals 1, minus 1, 0 plus 1, meaning there are 3 p subshells are possible. Okay, so 5p. So if you draw that 3p orbital, so this is in the 5p sublevel, there are 3 subshells. And remember, we learned about Hund's rule and the polar exclusion principle. When you are filling electrons, first you have to fill them singly occupied before you start pairing them up. So 5p2. And then we want to find out the quantum numbers for the highest energy, which is the last electron, that one. Now we're going to figure out what are the 4 quantum numbers, which is your N, L, ML and MS for 5p2. So the 5 represent here the principal quantum number N. So N equals 5. L is the shape of the orbital. Since the shape is P, L value corresponding to P is 1. So L equals 1. Okay, and there are 3 possible ML values. They are minus 1, 0, plus 1. It represents these orbitals. Now out of the minus, 0, plus 1, which orbital do you find the highest energy electron, which is in the 0 position? So that's your ML. So the ML going to be then 0. And the spin is always facing up. If you have only one electron, we always put it facing up. So the MS going to be plus half. So those are the 4 quantum numbers for the highest energy electron in tin. N equals 5, L equals 1, ML 0 and MS plus half. Okay. Alright, I think I'll stop here for the 1 to 9 and I'll start again in the next session. Let's see if I want to do number 10 and stop. Let's do number 10 also, because that is for the strontium. Since you have this information fresh, the next one is similar to this. So the number 10 is going to be strontium. Okay, number 10. Select the correct set of quantum numbers N, L, ML, MS for the first electron removed in the formation of a cation for the strontium. Now the previous one, it asked the highest energy electron, which is also the same as the first electron removed in the formation of a cation for strontium. Okay, so let's locate where strontium in the periodic table. Strontium is right here. Okay, now how can we write the condensed electron configuration? First, you're going to find out what is the noble gas prior to that, krypton. And then the strontium is in which period? 1, 2, 3, 4, 5, 5th period, right? Krypton, 5th period, this is the S1 and then fills the S2, since S can hold up to 2 electrons. So the condensed electron configuration for strontium would be krypton 5s2. Okay. Krypton 5s2. Number 10. Strontium is krypton 5s2. And we need to find out what are the quantum numbers in the highest energy, or the one that's going to lose first. So this is your 5s orbital. and maximum number of electrons S can hold is, any orbital can hold is 2. So the 2 electrons are going to be in the same orbital. The first one spin is facing up, the second one spin is facing down. Now you know what is the principal quantum number in 5s2? 5. And since S equals 0, remember L values could be 0, 1, 2, 3. Orbital designation S, P, D, F. If this is orbital is S, then the L should be 0. What are the possible ml values? You can have only one ml value, that is 0. ml is 0. And here we are talking about the highest energy, or the one that removes first is the one that is furthest away. The last electron that's been filled, that is the blue circled electron. And that we need to figure out the ms value, spin quantum number. Always the first spin going to be plus half, the second one facing down going to be negative half. So the ms going to be negative half. So the highest energy, or the one electron that loses to form strontium cation, the principal quantum number n equals 5, L0, ML0, and spin would be minus half, 500 minus half. Okay? Alright, I'm going to stop here 1 to 10, and then let's start the other part next session.